Well, I mean, the exciting thing to do would be some sort of electric vertical takeoff and landing, supersonic jet of some kind.
Vertical takeoff and landing, meaning no need for a runway. Just shoot up straight in the air and then...
Brace yourselves because the future of flight is approaching at an unbelievable speed. Elon Musk has unveiled a vision for a hypersonic aircraft that doesn't just push boundaries, it shatters them. What if a plane could do more than just break the sound barrier? What if it could redefine speed itself and transform how we connect across our planet? The ambition is staggering, and the implications are profound. This isn't just another plane, it's a potential revolution in the sky, and what you're about to see will stretch the limits of what you thought was possible. A glimpse into a supersonic past. This isn't science fiction. We've actually done it before. The Concorde flew passengers at twice the speed of sound for 27 years. From 1976 to 2003, it cut transatlantic flights from 8 hours to 3.5. Then it stopped, and supersonic passenger travel disappeared. Here's what the Concorde was and what killed it. To understand this legendary aircraft, we have to go back to a unique moment in history. In the 1960s, the race to conquer the skies wasn't just between companies, it was between nations. In a surprising move, two old rivals, Britain and France, decided to join forces. They signed a treaty, an actual government treaty, to build a supersonic passenger plane. That's how monumental this task was. They named it Concorde, spelling it the French way, to symbolize this new spirit of agreement. It was more than a plane, it was a political statement. And what a statement it made. The Concorde didn't look like any other airliner. It was long, slender, and graceful, like a white dart shot from the heavens. Its most famous feature was that incredible needle-like nose. But this nose had a secret. It could actually droop down. Why? Because the plane was so long and sleek that pilots couldn't see the runway during takeoff and landing. So, the nose tilted, giving them a window to the world below. It was a piece of pure mechanical poetry. But the real magic happened once it was in the air. Its wings had a distinct, sweeping, triangular shape, what engineers call an ogival delta wing. This wasn't just for looks, this special wing was the key to slicing through the air at unbelievable speeds. The Concorde could cruise at a sustained speed of Mach 2.04. That's more than twice the speed of sound, or about 1,350 miles per hour. To put that in perspective, a modern Boeing 787 flies around 560 miles per hour. The Concorde left it in the dust. It flew so high, at nearly 60,000 feet, that passengers could see the dark curve of space against the blue-rimmed atmosphere below. You were literally flying on the edge of the known world. The flight from London to New York, which takes about 8 hours today, took the Concorde just 3.5 hours. It was the only passenger plane that would arrive before local time, famously called arriving before you leave. So, with all this glory, why is it sitting in museums? The answer is that the Concorde's greatest strengths were also its fatal flaws. First, and most famously, was the sound. Breaking the sound barrier creates a sonic boom, a continuous, thunderous clap that follows the plane wherever it goes. It was so loud it could shatter windows on the ground. Because of this, people were furious. Governments quickly banned it from flying over land at supersonic speeds. The Concorde was essentially trapped over the ocean, drastically limiting where it could profitably fly. Then there was the fuel. The Concorde was a gas guzzler of epic proportions. It burned through fuel so inefficiently that even with its exclusive sky-high ticket prices, it was a financial nightmare for airlines to operate. It only had 100 seats, and you needed to fill every one of them with a wealthy passenger just to break even. Then, on July 25, 2000, Air France Flight 4590 crashed during takeoff from Paris. All 109 aboard and 4 on the ground were killed when debris on the runway burst a tire, sending rubber into the fuel tank. The fleet was grounded for modifications. When service resumed in 2001, passenger numbers never recovered. The crash gave airlines the reason they needed to retire an aircraft that had never made money. In the end, the Concorde was a breathtaking technological masterpiece, but a disastrous business. It was a symbol of national pride that never became a symbol of commercial success. It showed us the incredible potential of supersonic flight, but it also taught us a brutal lesson in economics and environmental reality. It proved that speed alone wasn't enough. The next generation would have to be faster, yes, but also quieter, cleaner, and smarter. The question was, could anyone ever solve the puzzle that defeated the mighty Concorde? A new generation of aerospace companies believes they can solve the problems that defeated Concorde. They have new materials, modern computer modeling, and backing from major airlines. The race to revive supersonic flight has begun. Boom Supersonic, the heir to the throne. United Airlines and American Airlines have placed orders for Boom Supersonic's Overture jet. Japan Airlines has invested in the company. These represent real financial commitments from major carriers betting that supersonic travel can succeed where Concorde failed. Boom's aircraft, called Overture, is designed to carry 65 to 80 passengers at Mach 1.7, still more than twice the speed of conventional jets, but slower than Concorde's Mach 2. Here's why that matters. This strategic choice is not a compromise, but a calculated masterstroke in pragmatism. While Mach 1.7 is phenomenally fast, slashing a flight from New York to London from 8 hours down to just about 3.5, it deliberately avoids the extreme engineering challenges of the Concorde's top speed. By not pushing to Mach 2, the temperatures generated by air friction are significantly lower. This thermal management is a game changer. It allows Boom to utilize advanced but readily available carbon composite materials instead of the exotic heavy titanium alloys the Concorde required. This makes Overture lighter, cheaper to manufacture, and fundamentally more efficient. It's a classic case of working smarter, not just harder, and it forms the bedrock of Boom's strategy to create a commercially viable aircraft, not just a technological marvel. However, a supersonic airframe is only as good as its power plant, and this is where the Concorde truly stumbled. Its Olympus engines were magnificent but flawed, derived from a military bomber program. They were notoriously fuel-thirsty and incredibly loud, both during takeoff and because of the sonic boom at cruise altitude. Boom learned from this critical failure. Instead of adapting an existing engine, an approach that would inevitably come with built-in compromises for subsonic performance, the company decided to start from a blank sheet of paper. They are developing a brand new, custom-designed engine program named Symphony. This engine is being engineered with 4 explicit, non-negotiable goals: efficiency, reduced noise, sustainability, and affordability. It is designed from the outset to run on 100% sustainable aviation fuel, directly confronting one of the most significant environmental criticisms of supersonic travel. Furthermore, its design incorporates specific features to drastically mitigate noise during takeoff and landing, which is absolutely essential for gaining permission from noise-sensitive airports around the world. This dedicated, purpose-built engine program is perhaps the strongest signal that Boom is addressing the root causes of the Concorde's failure, not just its symptoms. However, Symphony remains in the design phase as of 2024. No prototype has been built or tested. Developing a new jet engine from scratch is one of the most complex and capital-intensive endeavors in aerospace, typically taking over a decade and billions of dollars. This undeniably represents Boom's single biggest technical and financial risk. Before committing to the monumental expense of building a full-scale Overture, Boom undertook a crucial step in de-risking its technology: building a demonstrator. This is where Baby Boom, officially designated the XB-1, enters the story. The XB-1 is a 1/3 scale, piloted supersonic demonstrator that serves as a flying laboratory. Its purpose is not to be a miniature overture, but to validate the core technologies, tools, and supply chain processes in real-world conditions. The successful ground and flight tests of the XB-1 provided invaluable data that confirmed the accuracy of Boom's complex computer models and wind tunnel simulations. It proved their specific aerodynamic design, their use of composite structures for a supersonic airframe, and their integrated flight systems before the company committed billions to the final product. This methodical step-by-step approach mirrors the validation processes used by established aerospace giants, lending significant credibility to Boom's ambitious roadmap. The ultimate validation, however, returns to the opening fact: the backing of major airlines. The aviation industry is notoriously conservative and risk-averse. For a new aircraft model to succeed, it requires unwavering commitment from the carriers that will operate and maintain it. The pre-order agreements and strategic investments from United Airlines, American Airlines, and Japan Airlines are not mere letters of intent or conditional options. They represent a multi-billion-dollar vote of confidence from entities that have conducted their own rigorous due diligence. These airlines have scrutinized Boom's business case, its technology maturation plans, and its operational projections, and they have concluded that supersonic travel can be a profitable part of their future fleet. This external endorsement transforms Boom from a speculative startup into a serious aerospace contender, with a clear, though challenging, pathway. Their roadmap aims to roll out the first Overture prototype by the end of the decade, with the goal of making supersonic travel a regular, accessible, though still premium feature on major transoceanic routes. They are, by every measure, the current and most determined leader in the race to bring back supersonic flight, building their future not on royal lineage, but on cold, hard commercial logic and verified engineering progress. The rule changer and the dreamers. Boom faces one obstacle it cannot solve alone: the sonic boom. For 50 years, supersonic flight over land has been banned worldwide, but NASA's X-59 has already flown, and community noise testing over American cities is scheduled to begin soon. The goal? Prove sonic booms can be quiet enough to change those laws. This is where the story expands beyond a single company and enters the realm of high-stakes, government-led science. The key player here is NASA, and their mission is not to create a commercial product, but to change the very rules of the game. The X-59 is, without exaggeration, one of the most peculiarly shaped aircraft ever built. It looks less like a conventional plane and more like something from a science fiction novel. It's incredibly long and slender, with a beak-like nose that accounts for nearly a third of its length. Why such a bizarre design? Every curve, every angle is meticulously calculated to manipulate the physics of sound. The goal is to prevent the shock waves from the nose, wings, and tail from coalescing into the two loud, cannon-like blasts characteristic of supersonic flight. Instead, the X-59's unique geometry is designed to spread these waves out and soften their impact. NASA's engineers aren't trying to eliminate the sound entirely. That's impossible. They are trying to transform the disruptive boom-boom into a much gentler, more acceptable sonic thump. Imagine the sound of a car door closing in the distance. That is the ambitious acoustic target. The real genius of NASA's plan lies in what happens after the test flights. The X-59 will embark on a crucial campaign, but not with politicians, with the public. NASA will fly the aircraft over several dozen selected communities across the United States. On the ground, they will deploy sophisticated microphones and, just as importantly, they will survey the residents. They will ask people what they heard, if it bothered them, and if it would disrupt their daily lives. This community response data is the entire point. NASA will then take this massive, scientifically rigorous data set to regulators at the Federal Aviation Administration and international bodies. Their argument will be evidence-based. Our data shows that this new class of quiet supersonic aircraft produces a noise that the public finds acceptable. Therefore, the decades-old ban should be updated to reflect this new technological reality. They are building the legal and social case for supersonic travel over land. Together, this ecosystem creates a powerful synergy. Boom is building the plane. NASA is building the regulatory pathway. This multi-pronged attack on the problem makes the current supersonic race fundamentally different and far more likely to succeed than the go-it-alone approach of the Concorde era. The finish line isn't just a fast plane, it's a quiet, efficient, and legally permitted one. Challenges for a new supersonic era. Let's talk about the three biggest obstacles. The sonic boom. That's NASA's challenge with the X-59, which we just covered, but two other obstacles remain. Economics and environmental impact. These can't be solved by clever engineering alone. They are deeply entrenched challenges that strike at the very viability of a new supersonic age. The first of these colossal challenges is money. Let's be blunt. Going fast is incredibly expensive. Physics is not your friend here. As you push a plane through the air faster and faster, the drag or the air resistance increases dramatically. To fight that drag, you need to burn exponentially more fuel. Analysis of Boom's overture suggests it could burn 2 to 5 times more fuel per passenger than a modern, efficient jet like an Airbus A350. That's a staggering amount, creating a fundamental economic chasm that must be crossed. This creates what's known as the supersonic premium. Someone has to pay for all that extra fuel, the complex engineering required to withstand heat and stress, and the expensive advanced materials. That someone is ultimately the passenger. The operational costs are so high that early analysis suggests a ticket on an aircraft like the Overture would need to be priced about 38% higher than a current business class ticket to be profitable. To put this into a concrete dollar context, business class from New York to London costs roughly $4,000 to $6,000 round trip today. That would put Overture tickets at $5,500 to $8,000 or more. We're not talking about a small upgrade. We're talking about a product exclusively for the ultra-wealthy and a tiny fraction of corporate travelers. The dream of making supersonic travel accessible to everyone, of it becoming the new standard for long-haul flight, slams directly into the hard reality of thermodynamics and economics. For this to be a true revolution, and not just a luxury revival for a privileged few, companies will have to find ways to drastically improve efficiency that defy our current understanding of aerospace propulsion and airframe design. The business model itself is a high-stakes puzzle that must be solved before any airline will place a firm order. Finally, and perhaps most formidably in our modern world, there's the long and winding road of regulation, intrinsically tied now to the growing, potent pressure of environmental concerns. This is a two-front war that every new supersonic venture must fight, and it extends far beyond the sonic boom. Building a working supersonic jet is one monumental achievement. Getting it certified to carry paying passengers is another Herculean task. Agencies like the Federal Aviation Administration in the United States and EASA in Europe have a painstaking, years-long process to ensure any new aircraft is safe. For a completely new type of aircraft, with novel engine designs and unprecedented flight profiles, the process is even more rigorous and uncertain. There is no existing pre-approved rulebook for certifying a modern supersonic airliner. It has to be written from scratch through a collaborative and often arduous dialogue between the manufacturer and the regulator. This bureaucratic inertia alone can add years of delay and hundreds of millions of dollars in development costs. Simultaneously, the environmental scrutiny will be intense and unrelenting. The world is now hyper-aware of its carbon footprint, and the aviation industry is already under significant pressure to decarbonize. An aircraft that burns 5 times more fuel per passenger than a subsonic equivalent is going to face a firestorm of opposition from environmental groups, skeptical governments, and an increasingly climate-conscious public. The emissions calculus is simple and damning. More fuel burned means more CO2 released into the atmosphere. This creates a massive public relations and regulatory hurdle that the Concorde never had to face. Furthermore, the noise issue is not confined to the sonic boom at cruise altitude. Even if that problem is magically solved, communities surrounding airports will not tolerate significantly louder jets during takeoff and landing. Stricter local noise regulations have been a constant trend for decades, and a new supersonic jet would have to be not just quieter than the Concorde, but as quiet as or quieter than the latest generation of subsonic aircraft to gain community acceptance. The industry often points to sustainable aviation fuel, SAF, as the solution to the emissions problem. However, this is not a silver bullet available today. Global production of SAF is currently minuscule, accounting for less than 0.1% of all jet fuel, and it remains prohibitively expensive, often costing several times more than conventional kerosene. Relying on it to power an entire fleet of thirsty supersonic jets is a bet on a supply chain and a cost reduction curve that is still in its infancy. So the race for a new supersonic era isn't just about speed. It's a grueling multi-legged race against economics and a socio-regulatory environmental nexus. The companies that succeed will be the ones who can not only build a fast plane but also a commercially viable one and a politically and environmentally acceptable one. They have to solve all these interconnected puzzles at once. The obstacles are indeed immovable in their complexity, but human ingenuity has a way of finding a path. The question is no longer just if we can fly faster, but whether we can afford to, and whether the planet and its people will let us. How long it takes will depend entirely on progress in these two critical arenas. The roadmap to realities. So, we've seen the players, the technology, and the immense challenges. This brings us to the billion-dollar question. When does this supersonic future actually arrive? If you're hoping to book a ticket for your next summer vacation, you'll need to be patient. The roadmap to reality is a long and bumpy road, filled with both exciting milestones and inevitable delays. Let's start with the most talked about timeline: Boom Supersonics. Their plan is aggressive, and in the world of aerospace, aggressive often means optimistic. They are aiming for Overture's first flight in 2028, with the goal of carrying passengers by the end of the decade. It's a thrilling schedule, and if they pull it off, it would be a monumental achievement. But here's the reality check. Building a brand new type of aircraft with a brand new engine from scratch is arguably one of the most complex challenges in the modern world. It's a process famous for delays. The Boeing 787 Dreamliner was years behind schedule. Even the Concorde itself faced massive development hurdles. Beyond the technical challenges, there's the financial one. Boom will need to secure billions more in funding to see this project through to the finish line. While their progress is impressive, many industry experts view their timeline with healthy skepticism, expecting that the first flights are more likely to slip into the early 2030s. But while the planes are being built, another critical piece of the puzzle is slowly moving into place: the regulations. You can't have a supersonic revival without permission to fly, and here, there's genuine reason for hope. In the United States, the Federal Aviation Administration has officially begun the process of reconsidering the decades-old ban on overland supersonic flight. This isn't a change yet, but it's the essential first step. It signals that the government is preparing for a new reality. This move is heavily influenced by the upcoming data from NASA's X-59 mission. As that quiet supersonic aircraft begins its tests over American cities, the results will provide the hard evidence needed to finally rewrite the rules. This regulatory progress is slow, but it's moving in a clear and positive direction for the first time in 50 years. So, what's the final verdict? The honest answer is that a return to commercial supersonic travel is possible, but it is not imminent. The late 2020s and early 2030s represent the most optimistic time frame, and even then it will be a very limited affair. Think of it like the very first cell phones, incredibly innovative, revolutionary even, but bulky, expensive, and only for a select few. The first supersonic flights will be a niche, premium product. They will connect major international hubs like New York and London, and the tickets will be priced for business tycoons and the ultra-wealthy. The true revolution, the one where supersonic travel becomes something accessible to the rest of us, is a story for the next generation. The journey has unquestionably begun. The pieces are being assembled, but we are still at the very start of a long and ambitious path. The supersonic age is coming, but for now, we are still watching it take its first tentative steps. The future is fast, but for whom? After this journey through the past, present, and future of speed, one thing is crystal clear. The dream of supersonic flight is no longer a relic of the past. It's a vibrant, dynamic pursuit, powered by a new generation of engineers and billionaires who believe the Concorde was just the beginning, not the end. The passion is back, the technology is advancing, and the goal is more exciting than ever. We are standing at the edge of a new era, looking out at a horizon that seems a little closer than it did yesterday. But this new chapter comes with a hefty dose of reality. The path forward is still incredibly difficult, paved with financial, regulatory, and environmental challenges that are far from solved. And this leads us to the most important question of all. If and when this future arrives, who is it for? The undeniable truth is that the first act of this supersonic revival will be exclusive. These initial aircraft will be the flying sports cars of the sky. Incredible, thrilling, and built for a clientele that doesn't look at the price tag. They will be for business travelers on urgent deadlines and a tiny fraction of the global population for whom time is the ultimate luxury. For the foreseeable future, supersonic travel will be a premium experience, not a replacement for the affordable flights we all rely on. Even if Boom eventually builds 50 Overture aircraft, they would serve perhaps 500,000 passengers annually, a tiny fraction compared to the billions who fly on conventional aircraft each year. The ghost of the Concorde looms large here. Its failure taught us that speed alone is not enough. To succeed where it ultimately faltered, this new generation must learn from those mistakes. It must be not only fast, but also quieter, cleaner, and smarter. It must prove that it can be a sustainable and responsible part of our world, not just a noisy novelty. The race to bring back supersonic flight is, in the end, a race to answer a simple but profound question. Can we make the world smaller without making its benefits available only to a few? The journey to break the sound barrier has been won. The next journey is to break the barrier of exclusivity. The future is fast, that much is certain, but whether it's a future for everyone, that is the challenge that still lies ahead.